Hey, thanks for the introduction. Hey everyone, and thanks for sticking around until probably the last talk of the conference. I'm Venkat Narayanan, and I'll be speaking about the promise and challenge of machine learning in self-driving. Just a few brief words about Aurora. So Aurora is a self-driving car startup that was founded in early 2017 by three of the pioneers in the space. Chris Urmson, who was one of the founding members of the Alphabet self-driving team, and their CTO. Sterling Anderson, who led Tesla's Model X and autopilot programs, and Drew Bagnall, who is faculty member at Carnegie Mellon University, and also one of the founding members of Uber's self-driving car team. So Aurora's mission, in one sentence, is to deliver the benefits of self-driving technology safely, quickly, and broadly. And the last couple of years have been very exciting in terms of the progress we have made towards this mission, both on the business side and on the technical side of things. This is evidenced by some of the partnerships we have made with Hyundai, Byton, and recently Fiat Chrysler, and raising over $600 million of funding in our latest Series B round of funding, of which Amazon was one of our investors. Now, on the slide here, I'm showing you some videos that demonstrate our technical progress. So these are all videos taken from actual operation of the system, where the output of the perception system is superimposed on overhead videos. So now, rough weather is part of our standard testing procedures. The boxes in blue on the right are showing you stable tracks of vehicles. The boxes in gold are bicyclists that are being tracked by the perception system, and boxes in red are pedestrians. So these will be the colors that I use for the rest of the talk. And in the bottom row are videos showing the decision-making and planning system in action. So you can see making high-speed merges into highway speed traffic, navigating left turns at complex intersections, and navigating amongst a group of moving bicyclists that are really hard to predict. So I want to briefly talk about Aurora's development philosophy. And there's a phrase we use internally, which is fuel the rockets. So this actually comes from an old adage from Larry Jackal, who's one of the organizers of this workshop, from the old Bell Lab days, which is don't build ladders to the moon. So what this really says is that it's very gratifying to make incremental progress every day by building a ladder to the moon. But ultimately, what gets you there is to build rockets that sit on the launch pad for a really long time and then cross 250,000 miles in a very short span of time. And so the implications of that to self-driving are really that we need to be investing in the right infrastructures and pipelines that allow us to make that progress in that short span of time. So we are interested in getting autonomy out quickly and broadly. So that means learning has to be a key component of our architecture. And so Aurora's philosophy to learning is roughly threefold. We want to learn from experts. What that means is that our experience at Aurora has been that high-quality data is extremely useful in training machine learning systems, as opposed to large volumes of low-quality data. This is standard experience from most practitioners of machine learning, right? So we invest a lot of time in building the right tools for annotation and collecting high-quality training data. The second part of that is learning from demonstrations. So expert driving demonstrations are extremely valuable in understanding how to control and drive the car. And more importantly, corrections to driving, the autonomous system could drive, and every time the expert takes over, that's very valuable information as to what's going wrong and how to correct behavior. And the final part of our learning is from simulation and regression tests. So simulation scenarios serve as constraints on the autonomous system. So we want smooth and human-like behavior, subject to passing a battery of real-world and simulated test cases. Now, in machine learning terminology, these 3 points roughly translate to supervised learning, imitation learning, and reinforcement learning. And this is something which we'll come back to in the later part of the talk. So I want to divide this talk roughly in 2 parts. Briefly speak about our perception philosophy, and in the later part of the talk, speak about decision-making and how learning interacts with that. So why is perception hard? So this is a movie that shows the typical complexity of a scene in an urban environment. Again, the boxes in red are pedestrians, the one in gold are bicyclists, and the one in blue are vehicles. So you see there's a dense crowd of pedestrians, so the perception system needs to be able to track these objects and actors through occlusions, forecast where they would be at a future time, and not just their positions, but also their full state. We really need to understand how fast these actors are moving so the decision-making system can make appropriate decisions. So internally, we view perception as really a game of statistics, right? So we believe someday it might be possible to use just vision to solve the self-driving problem. But practically, we believe that multiple modalities really enhance safety and are a practical way to market. So what we do is we really optimize for excellence in each sensor modality and combine them to drive down the error rates, as opposed to relying on nearly flawless performance from just one sensing modality. So here's a slide that shows the kind of failure modes that you get from different sensors. There's radar operating in a tunnel. You have artifacts due to multipath and Doppler ambiguity. And camera clearly has problems in low light conditions and high dynamic range situations. And LIDAR has its own artifacts when operating in a snowstorm or picking up spurious sensor returns from vehicle exhaust. And so then the goal really is to judiciously combine all of these sensors in a way we can drive down the error rates and get to a high standard perception system that actually unlocks safe self-driving. And so this way of sensor fusion is a natural way to solve the long tail problem. And so the long tail problem really is what does the system do when it sees something that it's never seen before? Maybe there's a moose or some extraterrestrial being that shows up on the shoulder of the road. And the problem usually boils down to not hitting that thing, right? And the way to design a solution is to build sensors such as LIDAR, radar, and camera that can perceive all the matter around the vehicle, and whether or not they understand what that object is, to keep track of it over time so that the decision-making system can appropriately respond. So internally, we call this the no measurement left behind principle, which really says every sensor return ought to be explained as belonging to something meaningful. And so that allows us to handle the long tail problem. And the final part of the perception philosophy is that machine learning by itself is required but not sufficient for efficient self-driving. I think at this point, most people working on perception agree that it's not possible to hand-tune features to get the levels of performance that we need for self-driving. But by itself, machine learning is not sufficient. And so on this slide is a video that shows, the bottom part shows the machine learning detector in operation, where you can see the detections that are produced over time are kind of choppy. And the top half of the video takes those machine learning detections and feeds them into a multi-sensor, multi-hypothesis tracker that has some understanding of physics. Vehicles in the world tend to follow laws of physics. And so these are the kind of tracking systems that are used in the real world for launching rockets. And then you get really stable tracks that can now be consumed by your decision-making system. So the key idea here is that we need to architect the components in a way that learned modules can naturally feed into systems that conform to the nature of reality. So that really summarizes the perception philosophy, right? So we want multi-sensor fusion, no measurements left behind, and combine machine learning with rigorous engineering. So in the next part of the talk, I'll delve into some of the challenges with planning and decision-making. So why is decision-making a hard problem? I think Professor X showed a great number of videos that demonstrates the complexity of interacting with these actors in a game theoretic fashion. So here's an example video that shows an oncoming actor nudging into our self-driving vehicle's lane. And to us, it's obvious what's happening, right? So the oncoming actor is nudging around the bicyclist that's in their lane, and then they're going to go back into their lane, and we can continue on, right? So to a self-driving system, this can be extremely confusing. It has to first confirm that this actor is not violating his laws or not a non-compliant actor, and should not freak out and say that, oh, this is a non-compliant actor, I need to slam on the brakes and yield to this person. So human beings drive very smoothly and gracefully. This is almost like a graceful dance with other actors. And these are the behaviors that we should be aiming to replicate. And then there are actors that are simply non-compliant. On the left is a scenario where a bicyclist just cuts in front of the AV. They have no right of way there. And on the right is a situation where you have a pedestrian who's jaywalking into the middle of the road. Again, they have no right of way. Yet we need the system to be able to handle these situations in a graceful manner. So I guess to anyone who's worked on robotics before, and especially planning and decision-making, you probably have some experience tuning state machines or decision thresholds and config files, and you're typically left with this distraught feeling of building these brittle systems that don't really capture the human-like behavior. And so that's the key lesson here. So machine learning has to be integral to getting smooth human-like behavior, and we cannot rely on engineered state machines and hand-tuned rules. The second part is that machine learning, again, by itself is not sufficient. We need planning invariance for safety. Now, the idea of planning invariance is quite old. So what this really means is that, let's say there's a vehicle in front of the self-driving system, and if it were to suddenly apply a hard brake and come to a stop, then it would be nice if the AV can always slow down and stop behind the other vehicle. So this is an invariant that must always be satisfied no matter what. So imagine the planning invariance as kind of enforcing a constraint on what the machine learned system can do. And so I think now that it's clear that machine learning has to be part of decision making, the question is, why not take the tools that we are currently working on? There are really exciting times right now in machine learning applied to planning. There's excellent progress in especially reinforcement learning. We have seen the kind of progress we can achieve in games like Go, beating world champions. And so the natural question is, why not take reinforcement learning and solve the problem, right? Easier said than done. I think a lot of speakers have eloquently argued today why that's not so simple. And so in the rest of the talk, I want to motivate why imitation learning is instead a better approach. Why use imitation learning when you can just do simulation or reinforcement learning? So on this slide, here is Dick Fosbury. And in 1968, he completely changed how high jump works. This is a millennia-long sport where people typically would jump straight over the bar. And in 1968, Dick Fosbury pioneered a new way of doing this by jumping backwards over the bar. And ever since then, people have basically imitated that strategy. Now, if I translate that to machine learning terms, because what I'm saying here is that global exploration is really hard. And when we find a good policy, we tend to imitate that policy to reduce sample complexity. And so that's why imitation is a really good idea. And using expert drivers who can demonstrate really good behavior is the way we should be thinking about decision making in self-driving cars. Now, there are a couple of challenges when it comes to applying imitation learning to decision making. And I want to spend a bit of time giving a couple of insights into these. The first is that the actions that are demonstrated by experts are not random actions. They are purposeful, deliberate, and account for future outcomes. So in some sense, the experts are solving a planning problem in producing these actions. And that's something which we must capture in our learning. And the second is that the decisions that experts take they have consequences. So when you make a prediction on one particular sample, it's not that you're suddenly free of consequences of that. You now need to make predictions on the outcome of that sample. And this is slightly different from the statistical learning paradigm in machine learning. So let me jump a bit more into the first part, which is that the actions that are demonstrated by experts are purposeful. So this is work from Nathan Ratliff, which is over a decade old now. So let's say we have this outdoor terrain robot, and we ask a human expert to demonstrate how they would control this robot or drive it to its goal, which is marked by the cross and X, right? And so they demonstrate this path, which is the green dashed line that goes through the grass and avoids the rocks. So this is definitely not some random path that they demonstrated. In fact, what they're doing is that they have some objective in their head, which looks like, I think it's okay for the vehicle to drive over grass, but not rock. And so I'm going to use that objective to guide me to generate a path, right? And so in some sense, what they're doing is they have a cost function, they minimize that cost and produce this trajectory as a demonstration. And this is really a powerful way of modeling imitation. And if we can recover the cost function which the expert used, now we can use that same cost function to produce behavior online. And so what I described here is the idea of inverse optimal control. And this goes back all the way to 1960s in the control theory community, where Kalman first solved this problem. So the question is, if you have an optimal controller, what is the cost function that allows you to recover this optimal policy? And there are a couple of things we need to worry about when applying this to imitation learning. The first thing is you need a planner that can, given a cost function, produce a trajectory. So that's number one. And the second part is you want to be able to update this cost function so that that makes the human expert driver trajectory look as likely as possible. So these are two parts that you need. And it turns out there's a really good way to model a planner in that fashion. This turns out to be a maximum entropy model. And so what that really means is that every time you have a cost function, that immediately implies a distribution over trajectories. So you can attach to every trajectory a probability of that trajectory, right? So that looks like it's exponentially, it's proportional to the exponential of the negative cost. And what that's saying is that trajectories that are really expensive are really low likely, have low likelihood, and cheap trajectories are extremely likely. And so in this picture, I'm showing you a distribution of trajectories that's induced by a cost function here. So what this looks like is that you could have a sample of trajectories that continue following the lane where the vehicle is already in, or a distribution of trajectories that changes lanes, right? And now once we have this kind of a statistical model of your planning system, now we can go back, look at the human demonstrations, and update our cost functions so that the human driving looks a lot more likely under that distribution. So in some sense, we tweak parameters of our cost function, which in turn changes the distribution of trajectories that now makes the human trajectory look more likely under that distribution. So in some sense, this is the idea of maximum entropy inverse reinforcement learning, which has gathered a lot of momentum in the last few years. And now going back to the second part of this, right? The decisions that we make have consequences. In the traditional machine learning, statistical learning paradigm, your test data, training data are IID, so you can make a prediction on one example and go to a different example, make a prediction, not worrying about the result of the first prediction at all. So let me give you an example of a very classic imitation learning problem. So here you have camera images of a car on a test track. The speed of the car is fixed. So the only thing you can control is the steering angle of the car, right? So the one way you could learn a policy is to have a human driver. An expert drives this car around this racetrack multiple times, and you build up a data set. Data set basically is a set of pairs of this is the camera image, and this is the steering angle you need to apply, right? And once you have that data set, you can now train your favorite supervised learning algorithm and fit a model, learn a policy, okay? And let's say you achieve really good training error, maybe even really good validation error. You take this policy and then put it on the car, and what happens? Not so good. Why is that? So if you go back to the cartoon picture here, so what really happens is that as we start executing this policy, we diverge a bit from what the expert demonstrated. And now we find ourselves in situations that we have not seen before, right? And in some sense, in the machine learning setting, this means that the test time distribution is different from our training distribution. And there's also the problem of violating our IID assumption. And this is a problem in making sequential decisions. And in a theoretical setting, what you can actually show is that if your likelihood of making an error on a single prediction is epsilon, and if you make t consecutive predictions, that error rate grows quadratically in the number of time steps. And quadratics are often bad, maybe not if you're optimizing them as cost functions, but this is really bad. So you get really bad behavior and divergence from what the expert demonstrated. So is there any hope? The answer is yes. And in some sense, it's a very intuitive algorithm. So if I ask you what you would do, you'd say, I would go to the new states that I diverge to, and then ask the expert, what should I be doing in those new states, right? And what you really do is interact with the expert. You get feedback from the expert that says, how should I recover from this state? You take that data and then incorporate that into your learning. And so this algorithm is intuitive, and it's called data set aggregation. Let me walk you through those steps. So the first iteration of this is the same as I described. So you have an expert driver that demonstrates a trajectory. You build a data set, train your policy. Now you go back and execute that policy. And now while you execute that policy, you query the expert for what the right steering angle is at every time step, right? And that gives you new data. And you take that new data, combine that with all the previous data that you had, and retrain your policy. So you're basically aggregating your data sets, which is why it's called data set aggregation. And you keep doing this for n iterations, and magically you can now show that the number of I guess your expected error is bounded, is linear in the number of time steps and not quadratic. So I guess the intuition is that in the non-dagger setting, if you make one mistake, let's say you make a mistake at the first time step, it means that all your future time steps are going to be wrong. And if you make a mistake in the second time step, you're going to make t-1 mistakes. And when you add them all up, there's OT square dependency. And because of the dagger setting, where you can recover every time you make a mistake, it grows linearly rather than quadratically. Now, there's a very practical consequence of dagger in self-driving car. And what is that? It means that interventions or interactions with experts are really useful and important learning signals. So there's a very common misconception in the world of self-driving that programs should be minimizing intervention rates and measuring progress based on that. But low intervention counts really mean, from the dagger setting, very low learning rates and not really useful data that we're gathering. So in this example, let me start this video. So what happens here is that the self-driving vehicle comes to a stop, and then there's a pedestrian that starts to walk, and they're going to very shortly cross the vehicle. The expert takes over, and then they cross the road, and now the vehicle goes. So in purple, the purple box shows what the autonomy system would have done had the human driver not intervened, right? And so what happens here is that both the autonomy system and the human driver yielded for the vehicle correctly. But the autonomy system decided to be a little eager and start making progress as soon as the pedestrian was out of the way, whereas the human waited for a little more time. So this is the kind of natural behavior that we want our decision-making systems to capture. And this is where interventions are really useful in learning that behavior and tuning our statistical models of the planner. So, and again, this slide shows some of the end-to-end planning examples of what we can achieve with this technology. Right? On the top left is an example where we correctly react to a bicyclist cutting in. The plan in green is the one that we are executing, and the one in blue is a contingency plan. And on the top right is an example where we correctly yield to pedestrians and bicyclists before making a right turn. The bottom row are examples where the autonomy system correctly slows down in a very human-like fashion to slot in and make a lane change or a high-speed merge in a very comfortable fashion. So before I conclude, I want to very briefly talk about testing. There's obviously simulation, which is an entire topic of its own. But one cool thing I want to talk about is the idea of virtual testing. So roughly, the idea looks as follows. We have an expert driver who goes out and collects example data in really interesting situations. Right? So this is expert driving in an interesting bunch of situations. And now we can go back, use our statistical models of the planner, and ask the question, how likely is this human driving data under the model of the planner, under the cost functions that we currently have? And hopefully, if things are well, they say these are all extremely high likely trajectories, we have cost functions that model what the human is doing. And now, maybe 6 months later, someone makes a change to the software stack, maybe they change the detector model a little bit, and suddenly you see a ghost vehicle, also known as a false positive, that shows up in the middle of your track. And we can now ask the same question. We can ask, what is the likelihood of the human trajectory under this model? And the system is going to say it's very low likely, because if there's a track, the cost function is going to be active for the track, and I wouldn't expect the human driver to drive straight through that vehicle, right? And now we can identify very quickly a regression in the system, or identify an area for improvement. And this is a powerful way to use previously collected offline data of experts to validate the system in a continuous manner without even testing on the road. So in conclusion, I'd like to summarize some of the key points. We want to build the rockets and fuel them rather than building ladders and making incremental progress with hand-tuned rules. Second, machine learning by itself is not sufficient. We need to combine it with rigorous engineering. And for decision and planning making systems, we need to be using statistical models that can be trained from human demonstrations, accounting for the feedback issues. And finally, interventions are really important sources of data from which we can learn, and we should view them as such rather than measures of progress. And with that, I'd conclude and take questions. Thanks.